Hey physicists, we are going to talk about vectors today. So I wanted to start off with a little clip for you.
I'm applying for a new film go by the name of Vector. It's a mathematics quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
Okay, so that's just a little bit of cute, physics stuff. We're going to talk a little bit about how vectors work real quick, just to make sure that we're all on the same page, and then do a couple of examples. So, as he said in his little personal description, a vector has both direction and magnitude. Hopefully this will work. There we go. Okay. They're represented by arrows. The direction is obviously which way it's pointing, and the magnitude is represented by the size or the length of the arrow. When we're dealing with vectors, generally we talk about two kind of primary points. The first point of the vector is right over here. It's the part without the arrow on it, and that's called the tail of the vector. And the part up here with the arrow is called the head. Okay. And just like you can with scalars, numbers that just have magnitude, with vectors, we can add them. And generally when we add vectors, we do so I'm just going to write this down, adding vectors. We do so by lining them up head to tail. Okay. So that they kind of add up into pieces, or add up to give you a total. And when you add up the vectors, then the total is the overall vector. That's called the resultant. And the resultant is generally found by drawing one vector from the tail of the first to the head of the last. Okay, so that's kind of the very bare bones basic stuff in terms of the terminology. I want to look at a couple of examples with you that have to do with displacement, because that's the easiest kind of starting point, and then we will look at a forces example as well. So the first one that I wanted to look at here is an example about a minion named George. Okay, it says that he walks 4 meters north, then 6 meters east, and finally 12 meters south. So when we look at this, we're going to go 4 meters north, and I'm going to go ahead and draw a little vector there. And then 6 meters east, like so. So that arrow is pointed to the east if we think about our cardinal directions here, right? Never eat soggy waffles. Then we know that the pink one is pointing to the east. It's a little bit longer than the one pointing north because the magnitude is larger. And then finally, we've got a vector that is going south. That's 12 meters. I'll go ahead and mark these here. This is 6 meters, and this one is 4 meters. And our resultant vector, the overall vector, when we add these together, is going to go from the tail of the first to the head of the last. So it looks something like this. Okay? So when we're trying to find the resultant here, we basically need to find the length of it, we need to find a right triangle, because right triangles kind of tell us everything we need to know when we're talking about vectors. Okay, when we've got vectors in multiple directions here. So there is my triangle. My side over here, the shorter side, is going to be 6 meters, and that's coming straight down from there because those are the same length. And then as you can see, I went north 4 meters, I went south 4 meters. That gets me back to the same height up and down. And then I'm going to go south an additional 8 meters. So that's this piece here. So to find the magnitude of the resultant vector, I can do the Pythagorean theorem. So that's going to be a squared plus b squared equals c squared. Okay. And so in order to figure out this one, that's going to be my c. okay, or my resultant. So it's going to be 6 squared plus 8 squared equals, well, that happens to equal 100. Take the square root of that, gives me a C value of 10 meters. Okay, so that is the magnitude of the vector. I also need the direction because remember, a vector has both magnitude and direction. So a couple of things here, and this goes into a little bit more depth than the AP curriculum kind of requires, but I think it's important for you to see it. The angle that we're going to measure is this angle here, and that angle is always measured from the original location, okay? And we need to find that angle not only to say that he's located in the southwest quadrant, or excuse me, the southeast quadrant. I apologize here, because that could be anywhere over here. So that's, really an infinite number of places. I want to know the specific one, so I'm going to use my trig functions to find that. So I've got an opposite side of 12, or excuse me, of 8. That's this length here. And I've got an adjacent side of 6. I can use tangent. So I can say the tangent of theta is equal to my 12 meters divided by 8 meters. That's, again, opposite over adjacent. And using inverse tan, then we can say the inverse tan of 12 over 8. Oh my gosh, not 12. I'm so sorry, friends. That should be... Oh, silly me. I'm getting tired. I'm sorry. This is going to be 8 over 6. Sorry. I don't have you here to tell me that I screwed up. I just had to catch it myself. I apologize. Let me do that again. So we've got 8 meters here. That's the opposite. Adjacent is 6 meters. 8 over 6. 8 over 6. Inverse tan is an angle of 53 degrees. Okay? And that 53 degrees happens to be south of east. For our purposes, I'm not going to have you worry about this piece because it doesn't really matter. If you'd like me to go through that I'm happy to. The things that I want you to know how to do are to use the Pythagorean theorem to find the magnitude and to use trig functions to find the angle. Okay? So again, not going to sweat the other piece. If you want help with it, let me know. Okay? We're going to look at a second example here. Another minion here, Carl, has a total displacement, this one says, of 15.5 meters at a specific angle. So this is really getting to the heart of what we want to do for our purposes here. So I'm going to go ahead and put my coordinate system out there. And I know that the angle is 31.7 degrees north of east. Again, the label north of east, I'm not going to have you worry too much about, except to know that it's not at one of the cardinal directions. So it's 31.7 degrees like this. So here's my angle, 31.7 degrees, and my vector looks like this, and this is 15.5 meters. The piece that I want you to understand today is how to break this into components. So we've done components before, just wanting to remind you of how we did this. So we did components when we did our launches at an angle, okay? But just a friendly reminder so that you are feeling confident here, okay? We can find this side over here. This is going to be the part that's east, okay? And in order to find this, I'm going to call this X, okay? This is the adjacent side of our triangle. And then I've got my opposite side of the triangle right here. I'm going to go ahead and call that Y, or the part that's going north. So in order to find X is going to be the adjacent side. I know my hypotenuse and I know my angle. Adjacent, hypotenuse, and angle, that's cosine. The cosine of theta is equal to the adjacent side, that's the one I don't know, divided by the hypotenuse. So the cosine of 31.7 degrees times 15.5 meters will give us the part of the vector going in the eastward direction, okay? So 15.5 cosine 31.7 gives me a value of 13.2 meters, Okay, so that's this part right here, 13.2 meters. So when Carl took that walk with a total displacement of 15.5 meters at 31.7 degrees north of east, he could also have walked 13.2 meters east and then walked north. How far north, you ask? Well, we can go ahead and figure that out. So this is the opposite side. So I've got opposite and hypotenuse. That's going to be the trig function sine is opposite over hypotenuse. So we've got then 15.5 meters, that's the hypotenuse, times the sine of 31.7 degrees, okay? And that's going to give us our opposite side. So that's going to be 15.5 times the sine of 31.7. And we get a value of 8.14 meters. So this here is 8.14 meters. These make sense because they should both be smaller than the hypotenuse, okay? And their relative sizes kind of make sense given that angle. So that process of breaking into components is what will help us when we're doing our forces problems as well. So half of you have seen this problem before and the other half haven't. So if you haven't seen it, you might want to pause for a minute, take a look at it, get your head around what's going on, okay? So we've got identical treasure chests shown from above. So we're looking, it's like it's happening on a deserted island, right? Except there are maybe like two pirates that are fighting over this thing. We're looking at it from above and watching the results happen here. So in each of these cases, there is a 10 Newton force and a 6 Newton force that's being applied to the treasure chest. And the question asks for us to rank the speed of the treasure chest after 2 seconds. So we have to do a little bit of physics thinking here, don't we? So it wants to know the final speed after a time of 2 seconds. And we know that they all start at rest. So that means it has an initial velocity of 0. And it seems to me that if we're going to do that, if we need to find the final velocity, we might need to know the acceleration. So if we knew the acceleration, the initial velocity, and the time, we could find the final velocity, right? That kind of makes sense. We also, and we can find the acceleration by knowing the net force over the mass, okay? Now, these don't give the mass, but my argument to you is that if I can find the net force, and the net force is bigger, that to me would mean that the acceleration was bigger. And given what I know about final velocity, in that it equals initial velocity plus acceleration times time, if the initial velocities are all 0 and the times are all the same, the bigger the acceleration, the bigger the final velocity. So let me say that one more time. I want to rank the final velocities. If I know that the net force is bigger, then I know the acceleration is bigger. If I know the acceleration is bigger, I know the velocity is bigger. So really what this question is asking in kind of a roundabout way is for us to rank the net force. Okay, so let's take a look at the options here. B looks pretty easy. So let's take a look at that one first. I've got one pirate pulling 10 newtons one way, one pirate pulling 6 newtons the other way. So 10 minus 6 is going to be a 4 Newton force. This one happens to be to the left. But because I really am just looking for speed, I'm really just looking for magnitude. That's all I care about. So really this one just has a net force of 4. All right. All the other ones are a little bit trickier, so we need to do a little bit of thinking. Let's look at D next. It looks like the next simplest one. So in this case, this is where our vector addition comes into play, okay? So I've got one pirate that's pulling 6 newtons to the east, okay? And another pirate that's pulling 10 newtons to the north. The result is going to be a force in this direction, okay? Let's figure out how big that force is. We can do that by adding these together. So here's my 6 Newton force, and here's my 10 Newton force. And I can add those together and find a resultant. The resultant is going to be the net force acting on my treasure chest. So I've got 10 squared plus 6 squared. And I'm going to take the square root of that. Again, I'm just doing the Pythagorean theorem here. Okay. So the square root of 10 squared plus 6 squared gives me 11.6 newtons. The actual direction at this point doesn't really matter because, again, I don't really care about direction. All I want to know is magnitude because I just want to find the one with the biggest net force. All right, so I'm going to go ahead and list on for D that it's 11.6 newtons. 2 down, 2 to go. So obviously D is bigger than C, D is bigger than B. Let's take a look at A and C. So these ones take it one step further because unlike in D, where you had both forces acting perpendicular to one another, we've got forces in A and C where they're acting at funny angles. So we need to do a little bit more work, it looks like. So let's take a look at A. So I've got one force, the 6 Newton force, that's pulling directly to the east, okay? And then I've got this 10 Newton force that's acting both towards the west and to the north, if I'm kind of looking at it like that. So I'm going to break this part into its pieces here, okay? So I've got the force in the x direction, and I've got the force in the y direction, okay? It's a 45, 45, 90 triangle, so that's kind of convenient. It means to me that both of those forces are going to be the same size. Fx is going to be 10 newtons times the cosine of 45, also the sine of 45. 10 times the cosine of 45 degrees is 7.07. So that means that I've got 6 newtons pulling to the right and 7.07 pulling to the left, which really in the x direction is a net force of 1.07 newtons. But not only do I have that horizontal force, I've also got that vertical force going up like this, okay? This one is 7.07 as well, okay? Because that's the same as the Fx was. I'm going to draw this a little bit more legitimate, kind of like this. And so the resultant force here, I'm going to add those two pieces together. So 1.07 squared plus 7.07 squared, square root that, oops. And I get 7.15 newtons for my net force there. All right, we're almost there, friends. Last one. We're going to do the same kind of process that we did for A. I'm going to break this force that is in two different directions into those directions. So my x direction is going to be equal to 6 times the cosine of 45, and Fy is going to be the same thing. I can call it sine or cosine, does not matter. So 6 times the cosine of 45 is 4.24 newtons, okay? Then that is pulling, in the x direction, opposing the 10 Newton force. So I'm going to subtract the 10 from that. And so I've got a force of, in this direction, 5.75 newtons. And then I've got a force upwards of 4.24 newtons. And we'll do some Pythagorean theorem again to find a resultant going in this direction. So I've got 5.75 squared plus 4.24 squared. I'm going to square root that answer as well. And I get 7.14 newtons. So it looks like, assuming that I've done all my math right, and it's kind of late on a Monday night, so, here's hoping. We've got a force of 11. I'm going to call D the biggest. And then it looks like maybe A is next, then C, and then B. Okay? Friends, all of this process is exactly the same as we did in this first one, where we find a resultant, and in the second one, where we break it down into components. Those are the two pieces that you need to know, okay, in order to solve a problem that looks like that. Thanks so much. See you soon. If you have questions, you know where to find me.